Assalamu alaikum, dear students. Welcome to the new topic and the new section of the chapter 5. And there's a good news. This is the last section of the chapter 5, which is about evaluating definite integers with the substitution method and then finding area between the curves. So let's see how can we do it. So there is the section summary. First of all, we'll evaluate definite integers with substitution method, and this can be used in two ways. So one of the method is to find the antiderivative using substitution, as we learned in section 5.5. And then to evaluate the definite integral, we apply the limit using evaluation theorem, that is the fundamental theorem of calculus part 2. And the other method extend the process of substitution directly to definite integrals by changing the limits of integration. So if we make a substitution like gx is equal to u, then we find the limits for u using the limits for x. Okay, so we'll see in next slides how to find the limits for the new variable. And then we'll use this formula to compute the area between two curves. So first of all, substitution in definite integrals. So if g prime is continuous, that is the derivative of g is continuous on closed interval ab, and f is continuous on the range of gx is equal to u, then we have this definite integral of f gx into g prime x dx from a to b is equal to integral of f u du from GA to GB. See, limits of x are A and B. That is, this definite integral is evaluated in the interval AB, and when the function is transformed into u, then the limits, lower limit of u is GA, that is value G at A, and the upper limit of u will be value G at B. So let's have deep understanding of the method by with the help of some examples. So first example, evaluate this definite integral. You can evaluate directly if you have enough practice to integrate the functions. But I am going to make a substitution so that we can use how we can see how can we use the substitution theorem. So let's substitute. Now it's quite obvious. We have to substitute x cube plus 1 is equal to u. So let x cube plus 1 equal to u, because we have 3x square uh, times square root of x cube plus u. So derivative of x cube plus 1 is 3x square. So we have derivative of this function with us. So we can make the substitution. Now taking differential, 3x square dx is equal. Now the next step, which we were not doing in case of indefinite integrals. So if x is equal to minus 1, so the lower limit of x is minus 1. If x is equal to minus 1, what is the value of u? We just plug this x is equal to minus 1 into this relation. So u becomes minus 1 cube plus 1, and this is 0. And for x is equal to 1, that is the upper limit. For x is equal to 1, we have u is equal to 1 plus 1, and this is equal to 2. So this is now this integral can be written as lower limit of u is 0, okay, and upper limit of u is 2, and this integrand becomes u square root, and 3x square dx is du. So this is the new definite integral in terms of u. So let's evaluate it by power rule. So 1 by 2 plus 1 divided by 1 by 2 plus 1, and limits here are 0 to 2. So this is equal to u to the power 3 by 2 divided by 3 by 2, 0 to 2. So this is 2 over 3 u 3 by 2, 0 to 2. So this is equal to, after applying limit using evaluation theorem, so we have 2 by 3, 2, 3 by 2 minus 0. This is equal to 2 by 3, and this can be written as 2 square root of 2, and this is equal to 4 square root of 2 divided by 3, and this is the answer. Okay, let's solve another example. So here is an example of integration of trigonometric functions. So you can see that sin x is the derivative of cos. Cos x, derivative of cos x is actually minus sin x, so we can introduce negative here, so that it can be minus sin x. So let's make a substitution. Let cos x is u. Okay, then differential of this function sin x dx is du, minus sin x dx is du. So sin x, if we find the exact sin x dx, so this is minus du. Okay, so we don't need to introduce the negative sign to this. Okay, it will be automatically negative. Okay, now limits. Yes, next part. For x is equal to 2 pi, what is the value of u? Value of u is cos of 2 pi. Then u is equal to cos of 2 pi. Cos of 2 pi is 1. So when x is equal to 3 pi, then value of u is cos of 3 pi. Cos of 3 pi is minus 1. So we have this integral becomes 1 to minus 1 and 3 as it is, u square minus du, and this is equal to negative 1 to minus 1, 3 u square du. So let's introduce the limits. So 3 minus 1, 1 u square du, and this is equal to 3 u cube over 3 minus 1 to 1, and this is equal to of course 3 and 3, so we have u cube minus 1 to 4. So 1 cube negative minus negative 1 cube, so this is equal to 1 plus 1, and this is equal to 2, and this is the answer. Now there is another question, and let's try it without substitution. So you can see that this is actually the function gx. Okay, so what is the derivative of this function? G prime x will be 3 y square plus 12y minus 12, right? So this is the derivative of this function. So we have here y square plus 4y minus 4. So what we need to do in order to make the derivative of g, we have to multiply it with 3. So we will multiply it with 3 and divide it 3 as well. So let's try it without substitution. So we can do it directly as well. So 1 over 3, well, this is division by 3, and inside we have y cube plus 6y square minus 12y plus 9 minus 1 by 2, and when we multiply it by 3, this is becomes 3y square plus 12y minus 12 dy. So we have a function to the power minus 1 by 2 and the derivative of the function. Okay, so this is gx, this is g prime x, this is gy, this is g prime y. Actually, variable here is y. So this is gy, this is g prime y. Okay, now this becomes this is equal to direct, if we apply the rule of power. So we have rather than making a substitution, we have y cubed plus 6y squared minus 12y plus 9. Since we have the derivative of this function with us, then we can apply this, otherwise it is not possible. Plus 1 minus 1 by 2 plus 1. Okay, so this is equal to, and of course limits. So in this case we are not going to change them because we didn't change the variable. So 1 over 3, this is 1 over 2. So 2 over 3, it will make it 2 over 3. And now just plug in the limits. So when y is equal to 1, and this will become 1 over 2 as well. When y is equal to 1, we have 1 plus 6 minus 12 plus 9. Okay, and it will become 6 plus 1 is 7, 16. 16 minus 12. 16 minus 12 is 4. So 4 to the power 1 by 2 minus 1 by 2 plus 1 is 1 by 2. Minus, when we plug in 0, so all these terms are 0, we are left with 9. So 9 to the power 1 by 2. So this is equal to 2 by 3. 4 square root is 2 minus 9 square root is 3. So we have, this is 2 minus 3 is minus 1. So we have negative 2 by 3 is the answer. And you can try it with the help of substitution, and if you want to do this, you will have to substitute it. So let me tell you the substitution method as well. For this you have to substitute y cubed plus 6y squared minus 12y plus 9 is equal to u, and then taking derivative, we have 3y squared plus 12y minus 12 is equal to, dy equal to dj. Now we are required to find the value of this. So factor 3 out, we have y square plus 4y minus 4 inside. So this gives us the value of y square plus 4y minus 4 dy equals du divided by 3. So this is how you can make the substitution. And next we have to find the limits for u. So when y is equal to 0, so what is the value of u? U is equal to 9. And when y is equal to 1, then u is 4. So you can do it yourself to complete the solution, and you will find that answer in C. So this is exercise for you. Okay, next. Now in this case, let's make a substitution of 1 plus square root of y equals u. Okay. Alright, so what is the derivative of this 1 plus square root of y? 1 is actually constant, so derivative of 1 is 0. So what is the derivative of square root of y? It will be 1 over 2 square root of y. So we have dy as well, and this is equal to dj. Okay. So what else is required? Limits. So for y is equal to 1, we have u is equal to 1 plus 1 is 2, and when y is equal to 4, then u is equal to 1 plus square root of 4, that is 2, so u is equal to 3. So our integral is transformed into u as lower limit of u is 2, okay, upper limit of u is 3, and we have inside this whole becomes tiju, like you can see here. So this is tiju, and what is this? This is u. So we have 1 over u square tiju. Okay. So this is the new integral. Now, in order to evaluate this, just integrate it and plug in the limits. So this is actually 2 to 3. Let me write it in power so that we can use the power rule. So this is equal to u minus 2 plus 1 divided by minus 2 plus 1 and the limits for u 2 to 3. So this is equal to this is minus 2 plus 1, this is negative, and u to the power minus 1, that is we have 1 over u, and 2. So this is equal to negative sign outside, and we have by plugging in the upper limit we have 1 over 3 and minus 1 over 2. So this is minus just LCM, we have 2, we have minus 3. Okay, so we have 2 minus 3 is negative 1, negative, negative, positive, we have minus 6. Okay, if I haven't made any mistake in the calculation, then the answer is 1 over 6. And if you find some mistake in the calculation, pardon me and uh, correct it yourself. This is your exercise. Okay, next, different titles of symmetric functions. So you can see two figures. This figure A, the curve is symmetric about x-axis, okay, and the curve B is symmetric about uh, origin, right? And this is the actually curve of a function which is an even function. Now, what is even function? And a function is an even function if um, f of minus x is equal to fx. If we have a function fx, then fx is even if f of minus x is fx. Okay, so you can see whatever the point here for the positive a, exactly there is a point at the same distance, same height, the value of the function at x is equal to minus a. So similarly, if we have a point here, the value of the function is this, and if we take the negative of this value, say this is c, so this is negative c, and this is, of course, this height is f of c, if this graph is the function of fx. So you can see exactly at minus c we have the same height. So this is symmetry about y-axis. So if f of minus x is fx, the function is even, and even function is symmetric about y-axis. And in case of odd function, if fx is odd function, if f of minus x is negative of fx, that is height is going to be negative, right? So if we have a point here for value of x here, so this is if this is c and this is minus c, so you can see this is the height uh, f of c, maybe you can write it f of c, and this is the exact height but in negative sign, right? Because y is negative in this quadrant, so minus f of c, right? So this function is an odd function and it has symmetry about the origin. So the same point here, you can see the distance from the origin. Let me draw the line. Yes, this is from the origin, and you can join this. So this distance is same, and this is also same. So these 2 points lie on the same line. So this is the symmetry about origin. So if we have an even function or if we have an odd function, then we have a result for definite values, and this is the theorem. For even function, if we evaluate an even function in the interval minus a to a, in the interval minus a, closed interval minus a, then this is equal to 2 times integral from 0 to a fx dx. And it makes sense because uh, what does this integral mean? Area under the curve in the closed interval minus a to a, right? So since this is symmetric of outer x-axis, so the area covered under the curve from 0 to a is equal to the area covered under the curve from minus a to 0, right? So we can write this integral two times. We just evaluate the integral from 0 to a and we multiply it by 2. So this will give us the value of this. But in case of odd function, if f is odd, then what happens? Now if this is the area A, this is the area A, amount of area is A, but the sign of this is negative. Okay, this is the negative of this area. Similarly, if this area is B, this is the negative of this area. And what happens when we evaluate this integral, it will become 0, because a minus a, we are adding all the answers, so a minus a plus b minus b will be left with 0. So whenever the function is odd function, the integral from minus a, so keep this in mind, that minus a to a interval, right? So the limit should be minus a to a, minus 2 to 2, minus 1 to 1, minus 3 to 3, minus 100 to 100. Okay, so this is the key. Let's prove one of them. So this is the proof for the even function. So if f is even, we have to evaluate this integral from minus a to a f x dx can be written as minus a to 0 plus 0 to a. This is the split rule, additive rule, rule of addition of integrals. And by interchanging the limits, we can have minus 0 to minus a f x dx plus 0 to a. So we are going to do nothing with this. We have to just make it equal to 0 to a fx. So what we are going to do, we are going to make a substitution in this case. So x is equal to, make a substitution as x is equal to minus u, right? X is equal to minus u, that is u is equal to minus x. So x is equal to minus u will make us make the function f of minus u, and then dx is equal to minus du. We just learned we have to transform every value in the function. So dx is d minus du, and what about the limits? When x is equal to 0, u is equal to 0. When x is equal to minus a, u is equal to a. Okay, so our function becomes these substitutions are for this first integral. We're not going to change this one. Okay, this is for the first integral. Now just simplify it. This negative negative make it positive. So f of minus u du, since f is an even function. Okay, f is an even function. Then f of minus u is f of u. Okay, so 0, this becomes integral from 0 to a f of u du plus 0 to a f of x dx. Now this is u is dummy variable, so we can write it as 0 to a f x dx. So in case of definite integrals, this variable is dummy, because after applying the limits, we have the same answer, whatever the variable is, plus 0 to a fx dx. So it can be written as 2 times 0 to a fx dx. So this is result is true, that's there. So you can try it yourself in similar fashion. So do it yourself. Let's use the result to evaluate this integral. Okay, so you can see this is minus 2 to 2. The limit is minus 2 to 2. So a here is 2. Okay, so minus 2 to 2, we have to evaluate x4, evaluate the integral of x4 minus 4x squared plus 6. Now this function is even. How? Let's check. We have f(x) is equal to x4 minus 4x squared plus 6. So f of minus x is equal to minus x4. Just replace x by minus x in the function. So we have minus 4 minus x squared plus 6. Okay, and then we have uh, equal to x4 minus 4x squared plus 6, and this is equal to fx. So function is even. So when the function is even, so this is equal to 2 times 0 to 2 x4 minus 4x squared plus 6 dx, and this is equal to 2 times, now just integrate it and plug in the limits. So x5 over 5 minus 4x cubed over 3 plus 6x 0 to 2, and this is equal to 2 to the power 5 over 5 minus 2 cube, and 2 4 into 2 cube divided by 3 plus 6 into 2, and minus 0, by plugging in 0 it will make it 0, so minus 0. So this is equal to 2, 2 to the power 5 by 5 as it is, minus 2 square into 2 cube, it is 2 to the power 5 over 3 plus uh, 12, that is 2 square multiplied by 3, and it can be written as 2. Now we can take 2 square common, that is 4 common. So 4 is factored out. So inside we have 2 cube, that is 8, 8 over 5, minus again 2 cube, 8 over 3 plus 12. So we just have to simplify this. This is 8, and we have the LCM 15, 24, 40 plus 180, and we have 180 plus 24 minus 40 is actually 8, sorry, 8 over 15 multiplied by 164, right? And 164 multiplied by 8 is equal to 1312 divided by 50. So this is the answer, if I haven't done any mistake in the game. If I did, pardon me and correct it. So this is how we can apply the theorem, right? If a function is even function, we can use this result. So areas between the curve, finally we are here, application of integration, areas between the curve. Now if we have two curves fx and gx, and we have to find the area between the curve, shaded in blue color. Okay, so what we have learned so far, that if there is a curve, and by the help of definite integral we can find this area under the curve above x-axis bounded by the lines x is equal to a, x is equal to b. And how does it work? Actually, we divide it into sub intervals, and then we made it rectangles, and then we let the triangle, let the width of the rectangle to 0, in order to define the area. And this actually gives us the integral of fx. If we have to find the area of this portion, then this is integral of fx a to b, right, dx. So actually we are adding the heights, just we are running a line through this portion. Okay, and we are adding height of every line running through the portion, which gives us this integral. Okay, now same will go here. So we will run a line through this, and these heights, these infinite uh, heights will be added to evaluate the area. Now, how to do this? We'll just go through the process again. We learned in the evaluation of Riemann sum, and then converted it into the definite integral in terms of the limit. In limiting case, that is when the number of subintervals approaches to infinity, that is we are the rectangle is actually shrunk into a line. When the width of the rectangle approaches to 0, it means the rectangle is approaching towards a line. So that is why I was saying that we are actually running a line through the portion, and we are adding the heights of the infinite number of lines to form to find the area, this shaded area. Okay, so let's see. Let's subdivide the whole area into the smaller region, that is the interval AB, into sub intervals x0, x1, x1, x2, and so on. That is, we have a partition. So let's first do the partition of the interval AB, x0, x1, x2, xn, and this is shown in this figure. Okay, and then the same procedure, we'll choose the kth rectangle, and we'll find the height, we'll find the area of this rectangle, and letting the width of the rectangle to 0, we'll have the area bounded by these two curves. So let this be the kth rectangle. So height of this, choose any point in the interval, let it be ck. Then the value of f at ck is fck. So this is the point on the curve y is equal to fx at the point at x is equal to ck, and this is the point on the curve y is equal to gx, ck, gck, right? So the width of the rectangle, let it be delta xk, okay, delta xk, and let area of the kth rectangle be delta ak. Then delta ak is the height of the rectangle multiplied with the width of the rectangle. Height here is the fck minus gck, okay, fck minus gck. So keep it in mind, upper curve, the height of the upper curve minus the height of the lower curve. This will give you the positive answer, because y is increasing upwards. So value of the upper curve is greater than the value of the lower curve, right? So we always subtract the value of the function in this order. That is, upper curve, value of the upper curve minus value of the lower curve, height of the lower curve. You may say height of the upper curve minus height of the lower curve. So this is the height between the curves, fck minus gck, into width is delta xk, and then we add all these areas, and then we let n approaches to infinity, or the norm of p, that is the maximum width of the rectangle, approaches to 0, and finally we have area is equal to, and by taking this limit we have the integral a to b fx minus gx dx. By the definition of definite integral, we have this area. So formally we can write it as, if f and g are continuous with fx is greater or equal to x. So this is important, fx is greater or equal to x. Then we can write this order. If gx is greater than fx, then order will be reversed. So if f and g are continuous with fx is greater or equal to gx throughout the interval ab. So this is also important. This relation must hold throughout the interval. Otherwise, will have to break into pieces. So then the area of the region between the curves y is equal to fx and y is equal to gx from a to b is the integral of f minus g from a to b. So area becomes integral from a to b fx minus gx dx. So evaluation is quite simple. So I hope you understand the idea behind it as well. Okay, let's evaluate the area. So we have an example. Find the area of the region enclosed by the parabola y is equal to 2 minus x square. So this is the graph of y is equal to 2 minus x square and the line y is equal to minus x and the line y is equal to minus x. And we are not given a and b. In such cases, we have to find the point of intersection of both the curves in order to find the area enclosed by the curves if we are not given the limits. So in order to find the limits, we have to find the point of intersection. Now in order to find the points of intersection, what we need to do, we equate the heights. So y is equal to 2 minus x square in case of parabola and y is equal to minus x in case of line. So we need to find the points where height is same of both the curves. So 2 minus, for this, let 2 minus x square be equal to minus x. So we have x square minus x minus 2 equal to 0. So this is the quadratic equation and we can factorize it. So minus 2x plus x minus 2 equal to 0. So we have factors x minus 2 when x is factored out. We have x minus 2 inside plus 1 into x minus 2 inside equal to 0. So we have x plus 1 into x minus 2 equal to 0. That is, we have x is equal to minus 1 and x is equal to 2. So we have two values of x where height of the both the functions is same. Now in order to find the corresponding heights, we have to plug these values of x into any of the functions. So when x is equal to minus 1, we have y is equal to minus x, so y is equal to 1. So this is the point minus 1, 1. Okay. And when x is equal to 2, we have y is equal to minus x, that is y is equal to minus 2. So this is the point with height minus 2. So these are the points of intersection. Now we use the formula area. Now upper curve here is because value of this parabola at every point is greater than the value of this line at every point in the interval. So our interval in this case is minus 1. We have to check the values of x. So interval here is minus 1, 2. So we have to integrate minus 1 to 2. Upper curve minus lower curve. Upper curve is 2 minus x squared. Lower curve is minus x. So area is x is minus 1, 2. So upper curve here is 2 minus x square minus lower curve is minus x dx. So this is the area. Now we just have to evaluate, and which is very easy, you know it, how to evaluate. And we have 2 minus x squared plus x dx. So let's evaluate it. 2x minus x cube over 3 plus x square over 2 and minus 1 to 1. Okay, so when we plug in the upper limit, we have 2 minus 1 over 3 plus 1 over 2 and minus, let's plug in the lower limit, we have minus 2, we have plus 1 over 3 and we have plus 1 over 2. Okay, so this is positive 1 over 2, this is negative 1 over 2, so rest we are left with 2 plus 2 and minus 1 over 3 minus 1 over 3, which is equal to 4 minus 2 over 3 and which is equal to 10 over 3. 12 minus 2 over 3 is 10. So this is the answer. Isn't it easy? I think yes. Okay, and this is interesting as well. So application part is always interesting in calculus. Okay, let's have a look at another example, and there is a twist in this example. So find the area of the region in the first quadrant that is bounded by y is equal to square root of x. This is the y is equal to square root of x curve, and below by x-axis and the line y is equal to x minus 2. Below by x-axis, in this region it is bounded below by x-axis, and in this region it is bounded below by x minus 2. So bounded above by the function y is equal to x. So it has two parts actually. See, in this region from 0 to 2, it is bounded below by uh, x-axis, that is y is equal to 0, and from 2 onwards it is bounded below by the line y is equal to x minus 2. So it is very important for us to determine the regions or determine the limits to draw both the curves. So it will make your life easier if you draw both the curves. You can visualize it, and you can decide what to do. Okay, if you don't draw, you won't be able to actually visualize this type of the regions. So make it a rule that in order to find the area between the regions, you have to draw the curves first, and then you will use the formula given by the theorem we just saw. So we have to divide it into two parts. Now how to find these 2 points actually? Draw the line, you will have the intercept, and again I said drawing the curves will make your life easier in order to find the regions. So you will have the x-intercept of this line, which is 2. Okay, when y is equal to 0, x is equal to 2. So this is the x-intercept of this. So in order to find this line, this point, you have to find the point of intersection again, following the same procedure which we followed in the previous example. So let's find this point first. So let both the heights be same, that is square root of x is equal to x minus 2. So this will give us the point of intersection, and this implies x square is equal to not x square, x squaring both sides, we have x minus 2 square. Just solve it, you will have the point x is equal to 4. You will have two values actually, because this is quadratic equation, but you need the value which lies in first quadrant, that is the positive value of x. So positive value of x will be 4. Okay, so let me do it, and so that you can understand it. We have x is equal to x squared minus 4x plus 4, and we have x squared minus 5x plus 4 equal to 0. No, in this case this is not equal to 0. In this case this is equal to 0. Okay, now factorize it. X square minus 4x minus x plus 4 equal to 0. So taking x common, for factor x out, we have x minus 4 inside, and minus 1 x minus 4 inside equal to 0. So we have x minus 1 into x minus 4. Okay, and this is not the case. We have both the values positive, but for x is equal to 1, if x is equal to 1 somewhere lies here, these two curves does not intersect, right? So the point of intersection of the curves is going to be x equal to 4. Okay, so this is how we'll choose the point. Or as I said earlier, one of the values might have been negative, but in this case both the values are positive. But this figure shows you that this at x is equal to 1, both the curves doesn't intersect. So this is the point which is out of our range. So This is the point where both the curves intersect. So x is equal to 4, and for x equal to 4, how to find y? We just plug 4 in this equation, we have y is equal to 2. So this is the point, x is equal to 4 and y is equal to 2. So this is the point 4, 2, which is the point of intersection. Now for this region, now we subdivide this into two parts. For this region, area is, so let me first write, area is going to be uh, actually ABR. So let me write area, full form of area. So area, required area. Oh, okay, let me write required area, that is area bounded above y is equal to square root of x, below by x-axis, and the line y is equal to x minus 2. So first we write the x-axis part and then we'll write this part. So area, total area is the area of the region A, plus area of region B, and this is equal to, now we can use the integration form, 0 to 2, and this is nothing but the area above the closed interval 0 to under the curve square root of y is equal to square root of x, right? So or you may say this is area above x-axis under the curve y is equal to square root of x bounded by the lines x is equal to 0 and x is equal to 2. Okay, so this is, and this is actually simple integral 0 to 2 fx dx. So fx here is square root of x dx, okay, plus area of this region. Now limit of x from this region is this, or interval here is 2 4. So we have integral 2 4. Upper curve here is square root of x. So first we'll write square root of x. Lower curve is x minus 2. So square root of x minus 2 dx, right? So this is the problem we have to solve, and you know how to solve it, right? 0 to, this is square root of 2, that is x 1 by 2 plus 1 divided by 1 by 2 plus 1 uh, 0 to 2, and plus again x 3 by 2, let me write 3 by 2, 1 by 2 plus 1 is 3 by 2, actually 3 by 2 minus x square by 2 and plus 2x 2 to 4. Okay, you just have to simplify it to find the answer and simplify it yourself. My favorite part, do it yourself, okay, to find the answer. Just plug in the limits and you will have the answer. Okay, next, another form or another way to find the area. If the region's bounding curves are described with a function of y. So in the previous slides, we had the functions like this, and functions of x. This was the function of x, and this was also the function of x. Okay, but now in this case we have functions of y, that is x is equal to fy and x is equal to gy. Okay, so in this case, instead of dividing into vertical rectangles, we'll divide the region into horizontal rectangles like this. Okay, so if the region bounding curves are described by the function of y, approximating rectangles are horizontal instead of vertical, and the basic formula has y in place of x. And in this case, the difference of the functions will be right curve minus left curve, because this right curve has the greater value of x than the left curve at same value of y. Okay, so in this case we have a form y, and we have the value of x at that point, and we have the value of x at that point on both the functions. So right side is greater, has greater value of x than the value of x, left side, because x increases in right direction. So right value of x is greater than the left value of x, whereas the positive orientation of y-axis is upwards. So y increases upwards. That is why the upper curve minus lower curve, we had the formula as the upper curve, sorry, minus lower curve. But in case of the functions of y, then we have the because positive orientation of x is moving towards right, so right curve minus left curve. So in this case, lower curve minus, sorry, upper curve, upper curve minus lower curve. Then we have the case of value of case of x, function of x, that upper curve is also function of x, lower curve is also function of x, and here is the limit of x, so may x1, x2 maybe, okay. But in this case, right curve minus left curve. So right curve is function of y, of course, so this will be integrated with respect to y, and the limits are y1 to y2. So limits are also provided. So you can see the formal form of this formula. A is equal to integral from c to d. Of course, y varies from c to d. Fy minus g1. So f is the right curve. Okay, g is the left curve. So fy minus gy dy. Because f minus g will be the positive, because a value of f is greater than value of g. Then positive value will become from this difference, fy minus gy, that is right curve minus left curve, right? So this is the key, and rest is as usual. You have to integrate, but this time you have to integrate it with y, and you have to find the limit for y. So let's try the question, and we're going to solve same question in this method, using this method. In that part, we had to divide the portion into two sub portions. But in this case, there is no need to do this, because for every value uh, we have the line which starts from one curve and ends at the second curve. Okay, so we can run through the lines right. Okay, we can run through the line, the whole region actually, right? So there is no part of the region which is missing while running through the lines. So we'll just use the rule right curve minus left curve, and we'll find the area using the form x is equal to y square, that is x is equal to fy and x is equal to gy. So this is the y form. And what is the limit of y? Yes, this is the important part. What will be the limit of y? So y starts from 0 and ends at the points of intersection. Okay, this is the point of intersection, and at this point y is 2. So limit for y is 0 to 2. Okay, so what is the right function? X is equal to y plus 2, so we have y plus 2. And what is the left function? X is equal to y square. So throughout the interval, this function is the right function and this function is the left function throughout the interval. If any part of the interval, if in any part of the interval it doesn't hold, we have to subdivide it, as we did in the last version of the solution of this problem. Y plus 2 minus y square. Okay, d y. So this is equal to 0 to 2. So I mean, I should integrate it now. Y square over 2 plus 2y minus 5 cube over 3, and 0 to 2, of course. This is equal to 2 square over 2 plus 2 square minus 2 cube over 3 and minus 0 of course, and this is equal to 2 plus 2 minus 8 over 3, and this is equal to actually this is sorry, what happened? Actually this is 4, right? So we have 2 plus 4 is 6 minus 8 by 3, and this is equal to 10 by 3. So see, this is very easy to evaluate using this formula, that is in terms of y it's easier to evaluate. Okay, next we have this question: find the area of the region bounded below by the line y is equal to 2 minus x. This is bounded below by the line 2 minus x, and bounded above by the function y is equal to 2x minus x square. Okay, now I have different forms. If we are trying to find the area with respect to x, that is using integral with respect to x, we have this form. Okay, and this is hard to evaluate because of this radical function. Okay, so let's try other version with respect to y. And when we try to find the value of area with respect integral with respect to y, in terms of the integral with respect to y, then we actually ended up with this function, integration of this function. Again, this is complicated because of this part. So we can use the direct rule as well, because this figure is quite simple. This is 1, that is the 1 from 2, this length is 1, okay, and this here y is equal to 1, so this length is also equal to 1, and this is the curve, that is, this is the circular arc with radius 1. Okay, this is the circular arc with radius 1. Actually this is the 1/4 of the circle, quarter circle, right? So in order to complete the circle, you have to extend it like this. Okay, so this is the fourth part of the circle, 1/4 of the circle. So we with radius 1. So area of the circle is pi r square. So 1/4 of the circle is pi r square over 4. Okay, 1/4 of the circle. So we can find using, and this whole area minus the area of this triangle. So we are going to have area of this shaded region. So let's see how does it work. So we have because radius is 1, so radius of the circle will be pi. So pi by 4. The uh, this region actually, area of this region is pi by 4, and area of the triangle. This is the right angle triangle. Okay, with both the sides 1, so area of this triangle is 1 by 2. So we, from this whole region, we have to subtract the area of this triangle in order to obtain this area of this region in blue. So pi by 4 minus 1 by 2, so this is the answer. So this is easy directly, instead of evaluating the integrals. So sometimes we follow such rules, such direct rules as well, if there are any, of course. So finally, that's all for this section, and inshallah next time we'll start chapter number 6.1, which is about more applications of definite integrals. And till then, Bye bye. And yes, don't forget to practice the questions from exercise related to all these topics we have discussed in this lecture. And I'll urge you to try each and every question in the exercise, or one of the questions from every block. So there are blocks of similar questions. So at least a couple of questions from every block you should try, and you should try theory and examples as well. You should try word problems as well. So this is what I wanted to say as final notes. So take care. Bye.